So these are the notes that I've issued to you. Go back here. Okay. Can you see the notes?
Yeah.
Okay. So last week we talked about some other components in air systems that you're going to come across. The purpose, going right back to the start, the purpose of this training program was basically for new graduates who hadn't had very much experience or even no experience. But I guess most of you have had some experience already. Some have had a few years' experience. So we're probably going over things that some of you already know, but yeah, there might be some things you pick up in here that you weren't aware of, or it's clarified something for you. So that's the purpose of it. So we'll keep charging on. Today, this is the second last session in this series. We're going to talk about a few more systems that you'll encounter and talk about the applications of those. So it's energy recovery ventilators, dampers, various types of dampers that you're going to come across, VAV boxes, variable air volume boxes, and velogrids. I put velogrids in there because they're quite useful and they are commonly used in VAV boxes, but they're also used for other purposes, which we'll talk about in more detail. Oh, here they go. Morning, Stephen and Chock.
Good morning.
Welcome aboard. Okay, so energy recovery ventilators. These are basically air-to-air heat exchangers, which pre-cool or preheat incoming outside air by heat exchange with room air, which is exhausted through the heat exchanger. Heat exchangers are typically either a plate type, they call them a plate type heat exchanger, or a rotary heat wheel. The plate type are more compact and more or cheap to buy, obviously. Rotary heat wheels are very large and expensive, but have their application. And these heat exchangers can provide either sensible heat exchange only or sensible and latent heat exchange. The inside air load, as you know, can be quite significant, and particularly in summer and winter. So the ERV serves to reduce the load and provides energy savings, potential reduction in the air conditioning equipment capacity and cost. So if you've allowed for an ERV in your design, the outside air load on the air conditioning equipment will reduce, and that reduces the equipment size and the cost, and obviously reduces the operating costs if you can take out some of the outside air heat load. NCC Part J 5.3 specifies requirements for ERV systems. So this is important to be aware of, that it is a requirement of the NCC to use these in particular circumstances. The requirements are set out in Table J53, which I'll show you in a second, based on the climate zone of the project and the outside air flow rate. So this, again, for Ilias here in New Zealand, but we have similar requirements over there, but this is Australian requirements. The outside air flow rate may be controlled by modulating control, for example, CO2 sensing. If you have CO2 sensors in the space, you can modulate the outside air to maintain a certain maximum CO2 level, or use an ERV. So I'll show you that table, or that part of an NCC. Can you see that?
Yep.
Okay. So J5.3A2, when serving a conditioned space, except in periods when evaporative cooling is being used, where specified in Table J53, have an energy reclaiming system that preconditions outdoor air at a minimum sensible heat transfer effectiveness of 60%, or demand control ventilation, which is, for example, CO2 control. We'll look at this table J5.3, zones 4 and 6. Zone 6 is Melbourne, which is where most of you are. For an outside air flow rate of greater than 500 litres a second, you require modulating control or energy reclaiming system. So that's a requirement. And for other climate zones around Australia, these are the requirements. So be aware of that. Apart from the requirements of the NCC, it's beneficial to use these heat exchangers anyway. If you've got outside air, even if you don't have air conditioning, you might be able to use an ERV to reduce the. If you're bringing outside air into a room, it might help to reduce the heat coming in, or in wintertime to preheat the air coming in. So there's the example there. Melbourne, climate zone 6. If outside air flow is greater than 500 litres a second, the outside air must have modulating flow control or an ERV. And there's a couple of Australian manufacturers. There's also international manufacturers. One particular manufacturer, Armcore, is based in Melbourne. They manufacture units in a large range of sizes from airflows around 125 litres a second through to about 9,000 litres a second. So a big range of units are available. I'll put a couple of websites there, Armcore or AirChange, both Australian manufacturers of this type of equipment. And a bit of information about what they can do. In the plate heat exchanger range, the energy recovered under design conditions ranges from 2.6 kilowatts in the cooling mode, 1.9 in heating mode. That's for the small unit, 125 litres a second, through to up to 150 odd kilowatts cooling and nearly 200 kilowatts heating for the 9,000 litres a second unit. So the energy savings are significant. Rotary heat wheel models are available up to 8,000 litres a second airflow. Again, this is from Armcore, and can provide energy recovery up to 137 kilowatts cooling, 230 kilowatts heating. Now, just be careful if you want sensible and latent heat exchange. You need to check the data carefully as to whether those units can provide it. The rotary heat wheels will provide both. Sometimes plate heat exchangers can. Just make sure you're careful with the selections there. I'll show you a picture of some of those units. Does that come through? Morning, Dylan. So this is the Armcore small unit. You can just see inside the intake there. There's a fan there, and there's a plate heat exchanger behind that, which you can't really see. But there's the range of units available, airflow capacities. And this is a diagram of how the air flows through. So you've got fresh air coming in, the red one. Obviously, summer operation. Return air is a bit cooler. The heat exchange process occurs in here, and the return air is exhausted out of the building, and supply air is cooled down and supplied to the air conditioner or to the room. This is a picture of the large units. Again, it's a plate heat exchanger. And there's the range of capacities from 300 or 400 litres a second right through to 9,000 litres a second. And that's the process that occurs in there through again, just the cross-flow heat exchange through the plate heat exchanger. The fans included in the ERV units are EC plug fans, which can be speed controlled from the HVAC control system via a 0 to 10 volt signal. Some of the bigger units are provided with integral filters to protect the heat exchanger from becoming soiled. So when the outside air is coming in, it's going to bring dust with it. So filters are necessary on the outside air at least to keep the heat exchanger clean. If the filters aren't provided, the filter plenum is required, external to the unit. Some other features are available on the bigger units. You can get chilled water and heating water coils, return air bypass dampers, and economy cycles. Package units are available. So if you've got a job that's got a packaged air conditioning unit, you can get those with an ERV built into it. So if you've got a large outside air requirement, the swimming pool is a good application where you've got the ERV provided as well as compressors and a cooling coil to maintain conditions up to about 8,000 litres a second. So you can get them from Armcore or from Air Change. There's another manufacturer who's quite common in Australia called Munters. You'll find if you do a shopping centre that they may require Munters units. They're very sophisticated, complex units which can provide dehumidification, humidification, and so on. They usually come with a heat wheel. Excuse me. They'll have a rotary heat wheel, and they are quite expensive, but in some applications, that's what you need to use. The data for the ERVs will show a pressure drop through the unit. That's coded for by the fan, but they'll also specify an external static availability, which you need to take into account when you design the ductwork system. Any questions on ERVs?
With the term integral, does that just mean it's built into the unit? Integral
Sorry, Stephen, could you say it again?
You know how it says integral filters and integral fans? What does integral mean?
Inside the unit, yes.
Okay.
Yeah, some of the big ERVs have filters already supplied with the units. All the units have fans built into them, so you don't have to put fans in there. They'll always have fans in them. But some of the smaller ERV units don't have filters, and it's advisable to have a filter in the outside airstream at least to keep the plate heat exchanger clean, because they're very difficult to clean if they get dirty.
Peter, quick question.
Yep.
Can you explain the difference between the plate type and the rotary heat wheel heat exchange?
Yeah. So a plate type is basically a series of sheets, if you like, placed one on top of the other, and I'll go back to that. If you can imagine this dotted square here that says energy recovery, that's a series of plates laid one on top of the other. Fortunately, you can't. Well, you can probably see it on this diagram. On this, can you see this one of the large ERV? That blue element there is the heat exchanger, and if you can see that there's lines in between each plate, there's a series of plates. So the air passes through channels between all these plates. Okay. And so you've got air coming in and two air streams running parallel to each other, the fresh air and the return air, and they're traveling through different plates. Now, I don't know how they achieve that actually, but they separate the air streams, but the heat exchanges through the plate element, which in this case, that blue material, I think is a polypropylene material. Sorry, bit hard to get that out. I went to the Aero Show in Melbourne a couple of weeks ago, and they had one of the smaller ones on display. So they had all these parts pulled out of the unit on the table, and it was good to see that. Armcore, as I said, are in Melbourne. For those of you who are in Melbourne, they're very, very welcoming sort of people. If you wanted to go to their factory and have a look, it's over near the over towards Tullamarine Airport. They'd be happy to show you what they do and explain it to you in more detail. The rotary heat wheel, I haven't actually got a picture of that, but it's a big wheel. There's a separation in the unit between incoming and outgoing. You can probably Google it. Is that what you're doing at the moment, Hudson?
Yeah.
If you want to find something, we can have a talk about it.
Yeah. I think
And you finish up with a very large unit because depending on the capacity of the unit, they can be very, very large, like 3 meters diameter, something like that, and they rotate. So air is picked up on one side, or the heat is, let's say heat is taken out of return air on one side, and as the wheel rotates, it's transferred into the incoming outside airstream. And those plates, the elements of the wheel are usually coated with a material that absorbs moisture, so you get the latent heat transfer as well.
Okay, that was going to be my next question. Yeah, which one's for latent heat?
Generally,
or
the heat wheels are
humidification?
for both sensible and latent.
Yeah.
And you can get very small models of those as well. I know Munters have units that are very compact, probably airflows of only a few hundred litres a second. And they usually have a very small heat wheel. That's how they do it. But looking at this data that's in front of us here at the moment, you can see even with the plate heat exchangers, I saw a comment, options include, can you see those options here? You can get enthalpy or sensible media even with a plate heat exchanger. So they can apply a desiccant on those, so you can still get that as well. So there's a few options available, and this type of.
Hey Peter, sorry interrupting.
Yeah.
Will there be any condensation across this plate heat exchanger? Do we need
No,
no, not at all, right? Unless you've got
no, there's not. No, if there's any moisture exchange, all that moisture that's taken out of the one stream is absorbed in the other. So
What do you mean?
don't have you don't have condensation occurring. There is a transfer of latent heat, which is a moisture exchange. But there's no condensation because you haven't got a cooling. Well, if you have a cooling coil in the unit, yes, there will be obviously, but not through not through the heat exchanger.
Yeah, what happens if we intake like 6 degrees air and an exchange or extract 28 degrees moist air? Will there be any condensation? And imagine there is nothing, no heating coil, no cooling coil, just extracting and supplying.
Yeah, I don't believe so. I don't think condensation will occur in that situation. Good question. Probably worth looking into a bit further, but I haven't experienced that issue.
Yeah, because that question did come up because we're like, if you're recovering energy from toilets, let's say, and you've got all this moist toilet bathroom air, and then you're transferring that recovering heat to drier outside air, are you going to get humidification of that outside air, even if it's a sensible only ERV? And the question is, if it's sensible only, then how do they stop that from happening? How does that not occur?
Yeah, regardless is dry or not, if it's less than dew point you know,
Mm, yeah,
28, it was saturated with vapor. And if it's 6 degrees air hits the other side, then for sure there will be some kind of, or maybe the air velocity will take the humid out. I don't know. What is the general approach? They don't come with a drip tray, right?
I don't think so, no. But it's a fair point that if you've got air in contact with the surface that's below the dew point, then there will be condensation.
Yeah.
So it's yeah, I don't know. I'm not aware. I don't think they come with a drip tray. I've never put a drain tray on one of the condensate drain on one of these units. I'll follow that up and I'll let you know.
Awesome.
I'll find out about it and I can send out an email. I'll let you know next week. Good questions. Thank you. Anything else? I'll carry on. Dampers for flow control and fire and smoke safety. A damper is a set of blades or a plate that stops or regulates the flow of air inside a duct, VOV box, air handling unit, fan coil unit, or other air handling equipment. It may be used to cut off central air conditioning, heating or cooling to an unused room, or to regulate it for room-by-room temperature control. Damper operation can be manual or automatic. Automatic motorised dampers are used to regulate airflow constantly and are operated by electric or electronic motors in response to a signal from a thermostat or automatic control system, BMS or DDC. There's many types of dampers that you'll encounter in HVAC systems for flow balancing, control, isolation, and fire and smoke hazard safety. Some of the more common dampers that we come across regularly include manually operated volume control dampers, commonly called VCDs for flow adjustment and balancing, motorised VCDs for modulating volume control or isolation, manual operated butterfly dampers for adjustment of final flows to air outlets. There's a barrel damper. Motorised butterfly dampers for zone isolation or control, fusible link fire dampers, intumescent fire dampers, motorised fire and smoke dampers, air outlet opposed blade dampers, non-return dampers. It's important to provide clear access to all dampers to enable adjustment, inspection and maintenance. Now I'll go into these a bit more. So manual VCD, located strategically throughout the ductwork to facilitate adjustment and balancing of airflows during the commissioning phase. Manual dampers are turned by a handle on the outside of a duct while the airflow is measured either at the air outlet or through the duct using a pitot tube. When all the airflows are balanced, the manual damper can be locked in the set position to ensure the required flows are maintained. I've got a picture of one of those. That's a typical opposed blade VCD. The shaft here with a handle on it, you can adjust the blades. They oppose each other, which gives more accurate control. As one turns in, the other turns in towards it. And it's got 90 degree motion, and there's a locking quadrant there. So when you get in position, you can just lock it there and leave it set. The pitot tube, I mentioned a pitot tube there, so I'll show you a pitot tube. This is the pitot tube in the duct. It measures the differential velocity pressure, and from that you can calculate the airflow. And this is connected to a Magnehelic gauge, but in a site situation, this is not a very good photo. I couldn't get a better one, unfortunately, but can make it a bit bigger. The fellow there is putting a pitot tube inside a duct, and this instrument that he's got connected to it will actually give you a reading of velocity or airflow. So it can calculate the velocity pressure differential and convert that into an airflow. So he's measuring the airflow at various points in the duct, and then we'll do an average to determine what the airflow is in that section of duct. Manual VCDs are commonly installed at branches in ductwork to enable manual adjustment of airflows to the various parts of the duct system. So if you come out of an air handling unit or a fan coil unit and you have a branch that goes off, or a T, you've got air going one way or going in two directions, you would normally put a damper on each of those branches so that you can balance the air to each side. Supply air, return air, outside air, exhaust. Manual dampers are also installed in return air and outside air connections to air handling units and fan coil unit plenums to enable balancing of those two streams as they come into the return air plenum of the units. The most commonly used manual damper is the opposed blade, or OBD, which is the picture I showed you a minute ago, where the adjacent damper blades rotate towards each other to provide optimum control. Motorised VCDs, same as the VCD I just showed you, but with a motor on it. They can be modulating or open and closed to position. Modulating means that the damper position changes in response to a variable signal from the control system, and typically 0 to 10 volts DC. Typical uses for modulating dampers include return air and outside air control for economy cycle, so the allowing more air, outside air to come in and closing down the return air. Supply air flow control in response to a zone temperature sensor. So in the supply air duct, you have a motorised damper which responds to a temperature sensor. Duct static pressure control in a VAV system, and bypass control for coil bypass dampers or facing bypass dampers. So there's lots of applications for motorised dampers. I've got a picture of one. So again, can you see that? It's just an opposed blade damper with the shaft coming out, but this time there's a motor connected to it, which then is connected to the control system to vary the position of those blades. Typical uses for open-close dampers or two position. Closing the return air damper in fire mode operation and opening the smoke spill damper at the same time. So if you've got a multi-storey building, return air is going up a duct or a riser shaft, goes back into the air handling unit at the plant room, but also continues on to a smoke spill fan. So there's two motorised dampers there. There's one for the smoke spill, one for the return air. And in fire mode, return air closes, outside air opens. Smoke spill opens. Another example is opening the outside air dampers to fan coil units when they start and closing the dampers when the fan coil units stop. Sometimes if you've got multiple fan coil units on a floor or a space, you'll have a common outside air system coming to them, and they may have outside air dampers, motorised dampers to each fan coil unit. So if a fan coil unit is off, the damper can close. Then we've got butterfly dampers. Butterfly dampers are typically located in branch takeoffs or spigots, serving individual air outlets in supply, return, outside air and exhaust systems. The dampers are located inside the spigots, and flexible duct connects the spigots to the outlets. Again, the butterfly dampers have a 90-degree range of motion from open to close and are locked in the balanced position. So, picture of one of those. Close a few of these things down. So that's a typical spigot butterfly damper arrangement. One end of this is connected to your rigid duct, your main duct, and then a flexible duct is fitted to the outlet side, and the damper can be adjusted with this arm here and then locked in position when you've got the balance. You can also motorise butterfly dampers, often used for zone control, particularly in residential projects. The dampers are generally open or closed when zones are switched on or off, but they can be used as modulating dampers for zone temperature control. If you've got a small amount of air that you want to be able to have some control over and you don't want to use a VAV box, you can use a motorised butterfly damper. And I have a picture of one of those. Not a very good one, but there's a little motor sitting on top there. And in this case, your temperature control system is just driving or sending a signal to that motor to operate the damper inside the spigot. Now, air outlet OBDs, you can buy supply grills, return air grills with a damper on them, attached to them. So in a situation where you can't get to a butterfly damper in a spigot, for instance, if that's the case, if you can't get access to it, you might have to use an OBD in the grill. It's preferable not to, because they can be a bit noisy. As I said earlier, they can be useful for final balancing, but are generally of light construction and can create noise issues because they might rattle. And that's a problem that you can't do much about. If they start to rattle, it's very annoying. It's preferable to carry out balancing remotely from the air outlet where you can, using a manual butterfly damper in the branch spigot. So I'll show you a picture of one of these. So this is just, it's 50, this particular one is 58 millimeters high. It just sits on top of the grill and you can access it through the grill. So, and the blades work together. So if you can adjust it with a screwdriver and the blades will move, but they're very flimsy and they can be noisy. So it's an option, but probably not the best one if you can avoid it. Non-return dampers or backdraft dampers, used in many applications to allow airflow in one direction only. For example, if they're often used in the discharge duct from a fan to prevent backflow when the fan is not running. The NCC Part J 3.5 requires installation of NRDs when air is exhausted from air-conditioned spaces. So this is important to be aware of. An example is if the fan exhausts air from a printing area in an air-conditioned office space, there must be a non-return damper installed downstream of the fan. A lot of the fan manufacturers provide an option to provide an NRD with the fan, so that's worth taking up if you've got a situation where you have to have one. The NRD prevents both the loss of conditioned air as well as prevents leakage of unconditioned air into the space when the fan is off. So just to show you that requirement, where is it? That highlighted part there is from section J 3.5, which says that an exhaust fan must be fitted with a sealing device such as a self-closing damper when serving a conditioned space or a habitable room in climate zones 4, 5, 6, 7, and 8. So I just wanted to show you that requirement so that you're aware of what the requirements of the NCC are, that it is a requirement that you must do it in those situations. Okay, we'll move on to fire dampers. I'm sure you've all come across fire dampers. They're fitted where ductwork passes through fire compartment walls, floors or ceilings as part of a fire control strategy. The most common type of fire damper is a curtain top, which in normal operation, the damper blades are held open at the top, so the concertina are up to the top of the damper, and they're held in at the top of the damper by a fusible link. So I've given a couple of references there that you can go and look for more details, but I have got some pictures here that I can show you. If you haven't seen there's some fire dampers there. Can you see that diagram? This larger one shows the fire damper held in place at the top of the damper. For very small dampers in that situation, the fire damper will take up a fair percentage of the area of the duct. So you need to be aware of this, that there will be a pressure drop as the air passes through a fire damper. You're basically creating a sudden contraction and expansion at that point. So just bear that in mind, that there will always be a pressure drop of, maybe 10 to 15 pascals as the air passes through. That needs to be taken into account. When the fusible link is subjected to heat, such as in a fire, the link will break and allows the damper to close by gravity. So when that link's gone, it's at about 70 degrees Celsius, the link will break and the damper will fall down and close up the duct to prevent fire passing through. After a fire event, the fire damper can be reset with a new fusible link. But obviously, if you've had a fire, then maybe that's not possible. But if it's happened to close because it got hot, it closed, you can reset it. If there's been a major fire, then you probably need to start again and build a whole new system, no doubt. The link is attached to the damper in such a way that the damper can be released manually for testing purposes. So you can release the link and let the blades drop to ensure that the fire damper is working. The damper must be provided with an access panel in the adjacent ductwork for the purpose of inspection and resetting in the event of closure. So for some reason the damper closes, it could happen. There's the linkage breaks, or you've got to have access to it. And so you have access in the duct to get into the duct to get to the fire damper, but you also need access in the building, whether it's in a ceiling or a wall. And sometimes architects are reluctant to provide access for you, but you need to be fairly insistent on this, that you have to have access. The fire dampers need to be clearly identified on drawings and on site. So each fire damper has to be labelled on site, so it can be identified from a drawing. 20% of the fire dampers are required to be inspected every year, so that all fire dampers have been inspected at least once every 5 years. So the requirement is, I think it's AS 1851, that within 5 years, every fire damper has to be inspected. So you need to keep a logbook of inspections. That's why I say 20% every year. If you do a different 20% each following year, then you'll get through the whole lot in 5 years, because they can deteriorate over time and stop working properly. A logbook or record of inspections must be kept on site to show that the required inspections, including any repairs, have been carried out. Some other types of fire dampers, and there's various types, and you can have a look at those references I gave you for Selmec or Bullock and see the different types. You can get single blade dampers up to about 400 by 250. Again, they have a fusible link to allow them to operate. You can have multiple blade fire dampers, multiple parallel blades held open in normal operation by a fusible link. So it depends on your application. We haven't got time to go through all the details at the moment. I'm just trying to give you an idea of the various things and where to look for them for more information. Now, there's also intumescent dampers, which are quite useful. They have an internal grid, which is coated with an intumescent material. Intumescent means that when it's heated, it expands. Okay. In normal operation, air passes through the grid freely. In a fire event, the intumescent material expands and the grid becomes a solid block, preventing the passage of fire and smoke through the fire damper. So I'm sure you've come across these. These are a few typical examples. You can see the grids or the bars going across the damper. Well, they're coated with a material which, under normal operation, doesn't affect the airflow. But if it gets hot, if there's a fire, it will expand and completely seal up that opening. So after a fire event, the intumescent fire damper becomes redundant and cannot be reused. So it must be removed and replaced with a new damper. Once again, if you've had a significant fire, you're probably going to pull everything out. We'll start rebuilding. But in the event that that happens, yeah, you'd have to pull it out, which is not an easy thing to do. They're different to the curtain type fire dampers in that you don't need regular maintenance. There's nothing you can do with them. They can pick up dust from the building air and start to get a bit of a build-up and may create the resistance to the airflow. So you need at least to be able to have a look at them, maybe a small hole that you can inspect them to see what condition they're in, preferably a hole big enough or an access hole big enough that you can get a vacuum cleaner in there to remove some of that dust off them if there's a build-up. Because they're a little bit sticky, so they will gradually build up some dust in there and cause some restriction. Okay, smoke dampers. So in depending on the type of building, you might have smoke compartments in the building, and if a duct goes through that through the wall, you need a smoke damper. They're basically, smoke dampers are motorised volume control dampers with aluminium blades and high temperature seals. So it's basically a motorised volume damper, but with seals to prevent leakage. The smoke dampers are installed in ductwork within 600 millimetres of smoke-proof walls. That's a requirement in the Australian standards. It can't be greater than 600 millimetres away from the wall. And they prevent the passage of smoke from the fire-affected compartment to the adjacent compartment. And they need to be accessible for inspection and maintenance. So it's, I don't have a picture of a smoke damper as such, but there's a motorised damper. It's basically the same thing, but it has seals on the blades, on the edge of the blades and on the tips of the blades, so that when they close, it minimises leakage. And the leakage is a requirement. The maximum leakage is a requirement under AS. Can't remember the number. It might come to me. Sorry. In the fire testing code, anyway, they're required a certain amount of leakage is allowable. So the smoke dampers are normally open under normal operating conditions, but they'll close automatically if there's a fire alarm. They can also get motorised fire and smoke dampers. They're quite bulky. The combination of a conventional self-acting fire damper or fusible link fire damper and a motorised smoke damper. There's been a lot of controversy about these achieving the required leakage from the testing standard. I think now most of the main manufacturers have overcome that issue and that they can make these dampers that satisfy the leakage. So they're designed to not only stop the spread of fire between the fire compartments, but also prevent smoke from leaking from the fire-affecting compartment to adjacent compartments. An acceptable alternative, which is quite often the easier way to do it, in a ducted system, use a conventional fire damper in the wall or the floor, used in conjunction with a duct-mounted smoke damper, which again is got to be within 600 millimetres of the fire damper. That's usually the easier and cheaper way to do it. So there's some codes there if you want to go and read a bit more about it. Details for manufacture and installation of fire dampers, smoke dampers, combined fire and smoke dampers, etc., can be found in AS 1682, and maintenance requirements are in AS 1851. Any questions on dampers? Sorry, I'm rushing a bit now because I've noticed that we're getting close to time and I've still got a bit to talk about, but VAV boxes, variable air volume boxes. VAV box is basically a smart motorised damper in a purpose-built enclosure or a duct for controlling the airflow to a specific zone or room in a building. The position of the damper, hence the flow of air, is controlled by a zone temperature sensor via a central control system. Show you a picture. This is a Daikin VAV box. There's a damper inside the box, and there's a motor here which controls the position of the damper. And there's a feed in here from this is a VeloGrid, which I'm going to talk about in a minute. So I'll come to that shortly. VAV boxes are set up with a maximum and minimum airflow positions, and then the motorised damper modulates between the two positions in response to the controls. Maximum and minimum positions of the damper are controlled by an air velocity sensor, which is basically a pitot tube at the inlet duct connection of the VAV box. They can be furnished with either electric duct heaters or hot water heating coils to provide trim heating. There's lots and lots of different types of these. So I'll show you some of these. Selmec is a big manufacturer in Melbourne, the VAV boxes. There's various types available. A very basic one, it doesn't really show you the insides of it, but there's the duct. That shaft there is the damper shaft. You have a motor on there, controller. The inlet has the pitot tube for measuring velocity, so on. So you can get double duct types. This one's got an electric heater in it, and so on. So you can look up that Selmec website and have a look at those. So a typical VAV system comprises multiple VAV boxes connected to a common duct from a central air handling unit. So usually used for bigger systems. As the VAV boxes modulate, the duct static pressure will vary. A duct-mounted static pressure sensor will send a signal via the control system to the AHU variable speed drive to vary the fan speed to maintain a constant static pressure in the supply air duct. So you need something like that to maintain a constant pressure in the duct. Maintaining the required outside air flow rate can be an issue with VAV systems. The purpose of a VAV system is to vary the flow depending on the heat load. So if the heat load reduces, the VAV box will start to close and reduce the supply airflow. This in turn will reduce the outside air component of the supply air. So that can be an issue if you've got a VAV system serving a centre zone, for instance, where the supply air is dropping and the outside air is not sufficient for the occupancy of the space. So what you can do to mitigate the problem, using carbon dioxide sensors in the space, we can determine whether the outside air needs to be increased. If an increase is required, you can modulate the return air and outside air dampers on the air handling unit until the CO2 level drops below the acceptable limit. If the outside air flow requirement is designed to be constant and there aren't any CO2 sensors installed, a VeloGrid can be installed in the outside air duct to the air handling unit. I'm going to talk about VeloGrids in a minute. Again, it's like a pitot tube in the duct, but it's called a VeloGrid because it's measuring right across the whole duct. The VeloGrid will serve to maintain a constant velocity in the outside air duct by modulating return air and outside air dampers via the BMS system. So that's something that I have done in the past. It's probably not a common thing, but we had an issue in a hospital where we had VAV. It was quite a complex system, but we did have VAV boxes, but we were having an issue with controlling the outside airflow to some zones. So we put in VeloGrids in the outside air and modulated outside air and return air dampers. And that worked okay. So as I said, they're available in various types and sizes, including fan-assisted models. I thought I'd mention this one, which is used when constant airflow is required in the zone. So again, typically a centre zone where you want to maintain a certain airflow in the space. The fan-assisted VAV comprises a primary air VAV damper, a non-return damper, and an integral fan. So I'll show you a picture of one of those. In the Selmec catalogue, this is a fan-assisted VAV unit. You can have fans in parallel or in series with the primary air. So this valve here is that's the motorised damper. Primary air coming from the air handling unit is passing through here. There's a fan in here as well and a non-return damper. So if the primary air is being reduced because of the heat load in the space, then this fan will start. The non-return damper will open and allow air to come in through the ceiling space, return air from the ceiling, through the fan, mix with the primary air, and maintain a constant airflow in the space. So they're quite good for centre zones. As I said here, the design flow to each zone is based on the maximum heat load. Because the heat load is relatively low for an internal zone compared to perimeter zones, the supply air flow rate is also relatively low. We normally aim to provide 5 or 6 air changes per hour throughout. In the perimeter zones, you'll have no trouble with that, but in the centre zones, you need to be careful of that. When the heat load reduces, the standard VAV box damper will start to close and reduce the supply air flow, which may decrease below acceptable levels. The fan-assisted VAV box has 2 actions, as I've just explained before. So firstly, the VAV damper starts to close to reduce the primary conditioned air. And secondly, the internal fan starts, the non-return damper opens, and the room air is circulated to maintain the required air circulation rate in the space. That's a very quick talk about VAV boxes, but there's lots of different types. So if you've got a VAV system, have a look at all the data available and decide which one is the best one for you. Now, VeloGrids. VeloGrid, or a flow grid, is an instrument installed in ductwork to measure air velocity and hence the airflow. VeloGrid is basically an array of pitot tubes which provides an average differential velocity pressure and transmits this signal to the control system. The control system then responds by commanding actions such as modulating dampers to change position of return air and outside air dampers, or signaling a VSD to change the fan speed. There's 2 things you can do there. I'll show you a picture of a VeloGrid. Well, firstly, going back to the Daikin VAV box, that's a VeloGrid in the inlet. This is the air coming into the VAV box. It's got a VeloGrid in there. That sends a signal. It's a differential velocity pressure signal to this controller, which determines what the airflow is and takes the action necessary. There's some data on different types of VeloGrids available. So this box inside the ductwork here is basically an array of velogrids, which is sending a signal to a controller. Normally that goes to the BMS system to control the damper position. So there's various types shown there. Normally on a project, if you need velogrids, the controls supplier will be able to source those for you and put them in the ductwork. Common example for using velogrids that I've done on several occasions is in a hospital operating theatre or a lab or a clean room where you need a constant airflow and or a constant pressure regime where that needs to be maintained at all times. So in an operating theatre, you need to have a minimum amount of air changes. It has to be maintained all the time. You can't have variable airflow. And you need to maintain a positive pressure in the operating theatre with respect to areas around it. And this applies to labs and clean rooms as well. So in an operating theatre, as I said, you need to maintain a constant airflow rate and a constant pressure differential between adjacent areas. As the air filters collect particulates from the air, the filter pressure drop increases, which will cause the supply airflow to reduce. So in this case, the velogrid installed in the supply air duct senses a reduction in the velocity pressure differential, which is the airflow, and signals the fan motor variable speed drive to increase the fan speed until the velocity pressure differential set point is restored. So this process occurs continuously and seamlessly to maintain steady conditions in the space. So it works well. It's been done on many occasions. So I just wanted to mention those in case you've got a situation where you need to maintain an airflow rate. If you've got a lab or a clean room that you need to maintain constant flow, that's one way you can do it, by using dampers or fan speed control. It's 11 o'clock. I'll brace through it. You've got the notes to refer back to anyway, but are there any questions before we go? No? No questions? Are we having trouble with the transmission, or can you hear me okay?
No, it's all good. Yeah, no questions, I don't think.
Okay. Well, no one's asking any, so I'll let you go back to work. And next week is the last session in this series, which is about insulation of ductwork and pipework. And then there will be further sessions to follow, and I'll let you know about those either next week or a bit later on.
Awesome.